of finite state machine and regular expression and their application to the lexical analysis part. Here we will first discuss about lexical analyzer generator, Lex. So Lex is a lexical analyzer generator. It allows one to specify a lexical analyzer by specifying the regular expression to describe the patterns of the tokens. The input notation of the Lex tool is referred as Lex language, and the tool itself is called Lex compiler. The Lex compiler transforms the input pattern into transition diagram and generate code in a file called lex.yy.c that simulates the transition diagram. The use of the Lex. How to use the Lex? That we have a Lex compiler. We can give input lex.l file as a input, and it provides lex.yy.c as an output, and this lex.yy.c is a simple C program, and this C program can give the output by using the a.out. This C program provides the transition diagram, and finally once we have the a.out, it can provide, we can give the input stream, and it can provide the sequence of tokens. What is the structure of the Lex program? Let us discuss about the structure of the Lex program. The Lex program in the following form. Initially we need to provide the declaration, and then we need to write double 2 times percent symbol. Then we can have transition rules, and then we can provide 2 times percent symbol, and finally auxiliary function. So these 2 times percent divides the complete program into 3 parts. First part is the declaration part, second part is the transition rule part, and third part is the auxiliary function part. The lexical analyzer created by Lex behaves in the concert with the parser as follows. When called by the parser, the lexical analyzer begins reading this remaining input one character at a time until it finds the longest prefix of the input that matches one of the patterns pi, and it executes the action, associated action. So associated action should be written along with the each pattern. The lexical analyzer returns the single value, the token name, the parser, but uses the shared integer variable like yyl to pass the additional information about the linking found if it indeed. The declaration section includes the declaration of variables, manifest the constants, and the regular definition. The transition rules each have the following form: pattern, and then curly brace open, curly brace close, and inside that the action. The pattern is a regular expression which may use the regular definition of the declaration section. The action are fragments of the code typically written in language C, although many variants of the Lex using the other language have been created. The third section holds the whatever the additional functions are used in the action. Alternatively, these functions can be compiled separately and loaded with the lexical analyzer. So this is the structure. First we write hash include stdio.h. This is the simple part, and it is written with the percent symbol. Regular definition we can have here, and it is the letter. Letter can be represented by capital A dash Z, small a dash Z. Digit can be represented by 0-9 percent, double 2 times percent. Now it divides this part into the another part. If it is if we found if we, there must be the printf, that message should be printed the yy text. The yy text is the if part. Else, if we found else, then it will print recognized keyword is else, as the yy text is now else. So similarly, while do the whatever we want to do, the action should be, we should write in curly brace open and curly brace close in front of the curly. Now this is the new part: letter or digit asterisk. So obviously this is the part of the variable, and if the proper variable is given, then it should print the recognized identifier, and the identifier value will be printed. 2 times percent is given there, and then after that the third part starts. The third part of the program we write here int main, and we can have the yylex. We are calling the function yylex function, which is the init function. The steps to follow. How the steps can be followed? First we should use the vi editor, vi space lex.l, and then we should write the program. After that we should write colon wq, and then we need to print enter, and then we need to compile. To compile it, lex space lex.l. Obviously this program, the lex program, should be written in the file extension with extension l. Then we should write cc space lex.yy.c, and then we need to execute this part. So this is the structure of the Lex program. Another one more example is given. LT. LT is for less than, LE less than or equal to, EQ is for equal to, NE for not equal to, GT for greater than, GE greater than or equal to, if then else. All these things definitions are defined here. We can define the definition as many as we want. Delimiter is defined here. Backslash T and backslash N is given here. White space can be delimiter plus, which indicates that one or more than delimiter can be white space. Letter can be defined like this. Digit can be defined here. ID can be defined like this. Number can be defined like this. And again, 2 times percent is given here to bifurcate the next part. So if white space is there, no action is to be done. If, then if is returned, then token will be returned. If else is input, then else token will be returned. If there is ID, then this part will be executed, and so on. It can be written like this. So this is the one of the example which I am giving you. And there can be install id. Install id is a function that generally install the value which is found first time in the symbol table and then return the pointer to that, to there. So there can be install num. The number value numerical constant can also be installed in the symbol table. So this is the one of the example of the Lex program for the tokens. Let us consider about the finite statements. In Lex converts input program into lexical analyzer. The transition is formalized known as the finite automata. It is can be represented by a graph or by the transition diagram. So there are few differences. The first, the finite automata are recognizer. They simply say yes or no about each possible input string. Finite automata comes in the two flavor. First is the NFA, non-deterministic finite automata, and deterministic finite automata. NFA has no restriction on the label of their edges. A symbol can label several edges out of the same state, and epsilon it input string is possible label. DFA. DFA have each state for each state and for each symbol of its input alphabet exactly there will be one edge with that symbol leaving that state. The NFA consists of following part. It has five tuples. First is the finite set of states. Second is the set of input symbols. Third is the transition function. Next is the start state, and finally we have the final state. We can represent either NFA or DFA by the transition graph, where the nodes are states and labeled edges represent the transition function. There is a edge labeled A from state S to state T if and only if T is one of the next state for the state S and the input A. The graph is very much like the transition diagram except the following. The same symbol can label edge from one state to several different states. An edge may be labeled by epsilon, the empty string, instead of or addition to the symbol to the input alphabet. Example 1. First alphabet. Let us discuss. We want to have a regular expression for A or B asterisk ABB, which means that we need a finite automata ending with ABB. So this finite automata can be drawn like this, and its corresponding state can be written like this. AB, the input will be AB and epsilon should be added since this is the NFA. So this is NFA with epsilon. If the input state is 0, if we are at state 0, then if the input is A, we can reach at 0 state or 1 state. So it is written there 0 comma 1 in parenthesis, curly brace open and close. If the input is B on state 0, then it remains on 0, and if there is no change, then it went to 5. Similarly, if the state is 1, if we are at state 1 and the input is A, we are going to 5. If there is B, we are going to 2. If there is epsilon, we are going nothing, nowhere, so we can write here 5. Similarly, for if we are at state 2, then we should uh, take care of A, B and epsilon. If it is A, there is 5. If there is B, then there is 3. And for epsilon, there is 5. Similarly, for the state 3, A, B and C, we are going to nowhere. So this is the transition graph diagram for NFA recognizing the language of the regular expression A or B asterisk ABB ending with the B. Acceptance of input string by automata. The NFA accepts input string X if and only if there is some path in the transition graph from a start state to some of the acceptance state, such that the symbol along the path spell out X. Note that the epsilon label along the path are effectively ignored since the empty string does not contribute the string is constructed along the path. So let us discuss whether the string AABB is accepted by NFA in the previous example or not. So what we can do, we can move like this: AABB. If we are at a state, start state 0, 1, 2, and then 3. So 3 is the final state, so it is accepted. Note that the several paths labeled by the same string may lead to the different state for the instance path. अगर ये path लिया जाए, then what happens here? We lead to the another path. We remain at the state 0. So what we will do? We will ignore this part. If one of the path reaches at the final state, it means that that string is accepted. Similarly, the language defined or accepted by NFA is the set of string labeling from path from the start to accepting state. In above the example, NFA defines the same language as does the regular expression A or B asterisk ABB. So we can have an automaton L of A which identify the language. NFA accepting LAA or B asterisk. Since string AAA is accepted, so because of the following path, note that the asterisk epsilon disappear in the concatenation. So we can have like this part. So we have an FA accepting this language LA asterisk and BB asterisk. So this is another example. Let us consider about DFA. DFA is a special case of NFA where there are two things. One, there are no moves of epsilon. Second, for each status and input symbol A, there is exactly one edge out of the S. If we use transition table to represent DFA, then each entry is the single state. We may therefore represent thus state without the curly brace that we use to form sets. NFA, the abstract representation of the algorithm, recognizes certain algorithm, and DFA, concrete algorithm for recognizing strings of a certain language. Every regular expression and every NFA can be converted to DFA accepting the same language, and the DFA is implemented or simulated when the lexical analyzer is building. Simulation of DFA. The following algorithm shows how to apply the DFA to the string. Input is given this, output will be D, yes or no. The method is like this, the algorithm is like this. We can see here initially S is equal to 0, C equal to next char, while C is not equal to end of file. S move to S comma C, C equal to next char, so next character is found here. If S is in F, it means that if state is in final state, then return S, otherwise return no. So in this way we can simulate the DFA very easily. The DFA accepting L, A or B asterisk ABB string ABABB enters to the sequence like this 0, 1, 2, 1, 2, 3 and returns yes. We can see here in this case. So this is the second example of the DFA. So you have already learned this NFA and DFA in very detail in automata in the last semester. So we can skip rest of the part. Thank you so much.